So let us start. So good evening all. Uh, so just to give a brief background, since it is getting recorded and it will be uploaded for further reference. So is my screen visible? Is my screen visible? Please respond. My screen visible? So just to give a brief background, since it will be uploaded in the public forum. So welcome to the week 5 of problem solving session for the course Geotechnical Engineering 1, uh, uh, offered by Professor D.N. Singh from my Department of Civil Engineering from IIT Bombay. So I am Yogendra Narayanan. I am a PMRF research scholar who will be conducting these sessions. Essentially, these sessions are meant to make the learners of this course proficient in understanding the concepts that has been taught in a particular week uh, by solving some problems from the previous assignments and the previous questions uh, questions from examinations. And uh, furthermore, this these sessions, I hope it will be helpful the in a smooth preparation and for your exams, for your NPTEL exams, uh, as a base for any competitive exam preparations. And uh, so pretty much that's it. And uh, so this week, to give a brief uh, recap of what the course content that has been covered in the past week is the classification schemes of soil, essentially for fine grain soils, and various standards of classifications, namely uh, United Soil, Indian ASHTO, etc., and followed by consistency limits, uh, soil water interaction, uh, types of water, types of water present in soil, essentially, which is adsorbed, free, and phreatic, absorbed, and capillary, and followed by uh, some concepts, followed by a most important one of the most important concepts in geotechnical engineering and soil mechanics is the concept of effective stresses. So the calculation of effective stresses has been emphasized in the last lecture of this week. So based on these contents, we will be solving some of the problems and how to approach problems in under different circumstances, under given circumstances. So with this premise, uh, uh, so we can enter into the so we can start the problem solving session for this particular week. Uh, I hope the screen is visible. You can once confirm. Are you able to
Is visible, sir.
see the questions?
No, sir. Screen is visible, but not questions. Now it's visible, sir.
Now?
Visible, sir.
Now?
Visible, sir.
Okay. So, question number one. Let us start with a simple uh, questions, and then we'll be increasing the difficulties of these questions. So, Atterbuck limit is important for classification of which type of soil? Option A, coarse grained. Option B, fine grained. Option C, boulders. Option D, stones. Let me repeat the question. Atterberg limit is important for classification of which type of soil? Option A, coarse grained. Option B, fine grained. Option C, boulders. Option D, stones.
Fine grained soils.
Okay. Can you say what are all the Atterberg limits?
Liquid limit, plastic limit, shrinkage limit.
Plastic limit and
Shrinkage limit.
shrinkage limit. What is the other name for Atterberg's limits?
I don't know, sir.
Okay. So these
Index
uh,
properties? No, no.
index properties, it is common for coarse grained and fine grained. So Atterberg limits are also known as consistency limits.
Sir, your voice is struck.
Now is it clear?
Sir, your voice is not audible, sir. It's
Now?
breakdown.
Now?
It, now it's now it's audible, sir.
Okay. So these are known as consistency limits. These are also known as
Okay,
consistency
sir.
limits. Okay. So moving to question number, is it clear, right? Now are you able to see the screen?
Yes, sir.
So moving to the question two, the minimum water content at which the soil remains in liquid state and poses minimal resistance to their flow is option A, liquid limit, option B, plastic limit, option C, liquidity index, option D, shrinkage limit. Let me repeat the question.
Liquid limit.
Okay. Uh, why is it liquid limit?
The minimum water content at which soil remains.
Okay. Your answer, first question is fine grained, and this is obviously liquid limit. So we know that uh, first liquid limit, plastic limit, and shrinkage limit, as well as liquidity index. Not liquidity index. Liquid limit, plastic limit, and shrinkage limits are essentially water contents. So, uh, when minimum water content at which the soil remains in liquid state. That is when for example, when a liquid limit of a soil is 40%, that is when the soil reaches just 40%, the soil will start to behave as a liquid, and it will start, and this behavior will continue for water content greater than 40% also. So that is why it is a minimum water content at which soil remains in liquid state and poses minimal resistance to their flow. So when it is in liquid, relatively it is more flowable. It tends to be a slurry. So one more, we can extend this question. So what will be the shear strength of the soil at this liquid limit? Can you guess?
0.
Zero. Mm, here there is a one. So at this liquid limit state, at this exactly water content at liquid limit, shear strength will not be zero. Shear strength will be, there will be a slight presence of shear strength. Most of the soils shear strength will be approximately 2.7 kilopascal. It is an approximation. There will be a range, so 2.5 to 2.7 kilopascal. It is the shrink shear strength of the soil at liquid limit. Is it fine?
Uh, Sir, shrinkage limit and plastic limit, the shear strength is
No, that might vary, but that depends on soil to soil. But most of the soils at their liquid limit, their shear strength will be approximately 2.5 to 2.7 kilopascal. So it is valid
okay,
only
sir.
for liquid limit.
Okay, sir.
Fine.
Yes, sir.
Okay. So let us move to the next question. So which apparatus is employed for finding the liquid limit of the soil? Option
Third question is not visible, sir.
now.
Visible, sir.
So which apparatus is employed for finding the liquid limit of the soil? Option A, Leach Clears apparatus. Option B, Casa Grande. Option C, oven. Option D, none of the options. Let me repeat the question. Which apparatus is employed for finding the liquid limit of the soil? Option A, Leach Clears apparatus. Option B, Casa Grande. Option C, automatic oven. Option D, none of the options. So which is the right answer?
Casagrande apparatus.
Okay. How does it look like?
Sir, your voice is not audible.
Hello. Is it now audible?
Yes, sir, audible.
Uh, how does a Casa Grande apparatus look like?
Bowl,
Okay.
cup.
Okay. Okay. It is a. I will just uh, recap the procedure how liquid limit is found. So it is a bowl in which the soil is filled, and even and in that bowl there will be a groove made in the soil. So, and this will be connected to a uh, rotating device, and which will on rotation uh, which will move this bowl up and down, making it to hit the bottom plate. All right. Now, when the groove is made completely, and now at what blow this groove is getting filled up. So that number of blows are noted down, which is denoted as N, and the soil sample is taken out and it is dried in the oven to get the water content. So with this, we take at different at for different trials we do, and we plot it N in log scale and W in y-axis. We'll get the liquid limit is defined as the water content at 25 blows. So this is how liquid limit is calculated. I hope it is clear now. Right? Are you able to hear now?
Yes, sir, here.
So obviously the option is Casa Grande apparatus. Now moving to the question 4. What will be the y-intercept obtained if the linearly increasing portion of the graph plotted between volume of the sample V and water content plotted in a liquid limit test is extended to the y-axis? So what will be the y-intercept obtained if linearly increasing portion of the graph plotted between the volume of sample and water content is extended to the y-axis? There is a small uh, confusion here. So this can be neglected. This is a mesanomer here. So without this, the question will be there. So can you say what it is? Are you able to understand the question?
No, sir, once explain.
So what will be the y-intercept if the linearly increasing portion of the graph plotted between volume of the sample? That is, we are plotting a graph with volume as volume versus water content, right? So now, as this is water content 0, the volume will remain same to a particular water content, and then start increasing linearly. So what is this point called as? The point at which the graph starts to uh, increase linearly. Let us denote by A. What is point A known as?
Your writing screen is not visible, sir.
Are, are, are you not able to see the graph?
Yes,
What?
sir. No, no, sir.
Okay.
The graph is not visible.
Okay. Okay. Now,
Now it's visible, sir.
okay, now you are able to, can you say what is the point A now?
Shrinkage at shrinkage limit.
It is shrinkage limit. So after that, it start linearly increasing at a higher water content. It will this is uh, this is a it will be a solid matrix. It will be a it will be in plastic state. It will be in semi-solid state. So this is shrinkage limit. This is plastic limit. This is liquid limit. Here it will be in liquid state. So the question asked here is, this is the linearly varying portion, right? This part. Are you able to understand?
Yes, sir.
Now, if you extend this portion, that is what is being asked. What will be the y intercept? Intercept means at a particular point. So if we extend this, we will get a particular volume here. So what is this volume known as?
Volume of solids.
Yes. So that is, if you dry completely, the volume remaining at 0% water content is only volume of solids. And what will be this one? This portion. Can you say? So what will be this portion?
Volume of solids.
No, that is uh, the bottom portion. Top portion, what will be the top portion? So this is total volume. This is volume of solids. What will be the remaining?
Volume of voids.
It is volume of voids. When it reaches this point, shrinkage limit, volume of voids will be equal to volume of water. So, and this is the condition. So, the answer for this one is, they are asking y intercept. Intercept is measured from the origin. So, it is volume of solids. So, option C is the right answer. I hope it is clear.
Yes, sir.
So, now let us see this question. So, which parameter can be found by calculating the slope of the graph depicted below? Option A, toughness index. Option B, flow number. Option C, flow index. Option D, thixotropy. Which parameter can be found by calculating the slope of graph depicted below? Option A, toughness index. Option B, flow number. Option C, flow index. Option D, thixotropy. And
I
this,
think flow index.
yes, it is flow index. What is
Sir,
the,
fifth question and
yes,
sixth question. Question number.
there is a small, uh, there has been a small mistake here. So it has been, there is a rearrangement. So don't worry, we will be
Okay, okay, sir.
solving. So what is the relation for flow index? Flow index is depicted by IF. So it will be, if we take, let us take this point. This is W1. This, sorry, this is N1 and W1. So this is W2 N2, and this will be in log scale. This is a semi-log plot. So flow index is defined as uh, W2 minus W1 by log N2 minus log N1, which will be equal to W2 minus W1 by log N2 by N1. Hope it is clear now.
Sir,
Yes.
I W1 minus W2, I think.
No, that uh, s- uh, slope will be, uh, see, this slope is negative. So when you do it, it will be in, just a minute. N2 is lower. No, actually, hello. So flow index, this is just a magnitude. So we need to worry about the uh, uh, magnitude of slope only. So we will solve the problem. That time you will be more clearer. So, but the slope is calculated
Okay.
as this. Uh, it is a simple calculation of slope of a straight line. So it is a flow index. And moving to the next question, those who have joined, you can start solving from the question 8, and the previous questions, obviously, it will be uploaded in the problem solving session section of the NPTEL interface. From that, you can see the other slides. So after performing several tests on a soil sample, it was found that the plastic and liquid limits are 26% and 42% respectively. Calculate the plasticity index of the soil and determine its degree of plasticity. Let me repeat the question. After performing several tests on soil, it was found that its plastic and liquid limits are 26% and 42% respectively. Calculate the plasticity index of the soil and determine its degree of plasticity. I hope the screen is visible and the my my voice is audible. Those who have joined recently, can you please confirm?
Yes, yes, sir.
Okay. So can you say the answer for this?
Yeah, 16% in high plastic.
Medium plastic.
Okay. Which is the right option?
Yeah, medium
On
plastic. Yes,
option
yes.
B.
Hmm. B.
So plasticity index is liquid limit minus plastic limit. Plastic limit, and it will be 16%, rightly said. And here, based on the chart given in the lecture, it will fall under medium plastic. And for detailed classification, what you can do is you can overlap this value in the A line chart. I hope you are aware of the A line chart. It is a plot
Yes, sir.
between liquid limit and plasticity index. There is a there will be a line. Uh, there is a we will discuss it very shortly. So as far as this problem is concerned, it is 16% and it is medium plastic. So moving to the next question. In a liquid limit test, the moisture content at 15 blows was 60%, and that at 35 blows was 150%. What is the liquid limit of the soil? Let me repeat the question. In a liquid limit test, the moisture content at 15 blows was 60%, and that at 35 blows was 150%. What is the liquid limit of the soil? So there is a catch in the question. Uh, the question is now, let us extend this question uh, to two parts. So those who are answering the question blindly, so there is a logical question here. Uh, there is a shuffle of there is a contradictory in this in the statement of the in the question statement. Can anyone point out? Those who are solving it, can you point out what is the contradictory statement here? Are you able to get the catch here?
Liquid limit is find out at 25 bowls.
That you can find out from here, but there is a fundamental deviation from a logic here.
Okay. In the above data, we find out the plastic index. No, 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 no.
Any others?
In above data, we find out the flow index.
Hmm. That and these are not related. So that you will be using it, but there is a fundamental deviation from logic here. Can any other point? Can other people point it out? If you have no idea, you can that also you can say. If you don't respond, I cannot come to a conclusion. So
No idea, sir. Explain, sir.
okay, so here, what does this corresponds to? It corresponds to the number of blows at which the groove gets closed. So here, one in the same soil at at one moisture content, the number of blows is 15, and at the other for another water content, the number of blows is 35. So which should have the higher water content?
15 blows on 15 blows.
15 blows should have higher water content,
Higher water content.
and 35 should have lower water content. Now you interchange the values and you solve the question now. Now we know at 15 blows and 35 blows what is the water content. So we know that the slope of the line is linear. So this is water content. Sorry, this water content. This is the at 15 blows. The water content is 150, and at 35 blows, the water content is 60. So what is the slope is y2 minus y1 by x2 minus x1. So y2 is 60, y1 is 150, x2 is log 35 by 15, which will be equal to this water 150 we know, this water content we don't know, that is liquid limit, by log of, we know that at liquid limit the number of blows is 25, and for 150 it is 35. Sorry, it is 15. So now you can calculate it. Can somebody say the answer? Can somebody say, has someone completed
A
solving the
one
question?
zero A 105%.
Okay, any other?
One 14.
Yeah, any others?
114.
Okay. So the right option is 114.
Yes, sir.
Uh, so those who got 105 can please check it once again, and you can uh, so always, so the hint here is
Sir,
always, yes,
one mistake is
yes, please,
there. WL minus 150 by
yes.
log
Hmm.
35 by 20.
Okay, okay. 35 by 25. Hmm.
Yes, sir.
Hmm. No, no. Fine. Okay. So
Thank
it will be 114, and you just, you can always look whether the question is also logically right, and please proceed it. So even in the examinations, there might be some situations where this might be given as a check. So please proceed very carefully here. And moving to the next question, if the slope of the graph plotted between water content versus number of blows, that is whatever we saw in the earlier question, is steeper for a soil A compared to soil B, what can be inferred from this? Option A, soil A soil A has a higher reduction of strength with increase in water content. Option B, soil A has lesser shear strength reduction with water content compared to soil B. Are you able to get the question? If you are confused with the question, please let me know. I will
And
explain it.
answer is B.
Okay. Are everyone getting this? Or any confusion you are facing in the statement of question? Are you able to uh, understand the question? Others can respond.
Sir, explain it, sir.
Okay. If Okay, let me explain it once. So earlier we have seen that this is the liquid limit curve, that is plot. Now what they are saying is there are two soils for which the graph for soil A is steeper than soil B. So this is A and this is B, right? So now let us take two situations for both the soils. So before that, the fundamental notion is with that is the slope of the curve is flow index. So flow index is inversely proportional to shear strength. All right. Now So obviously we know that if IF is higher, shear strength will be lower. That is one inference of it. But this compared to related to this question, we have what we have seen is if we are taking two water contents and same here and two number of blows, and another water content here, so when the slope is steeper, uh, initially the number of the interval between the change in water content to the change in number of blows is higher. That is, uh, when water content decreases drastically, the n value does not change much in case of soil A compared to soil B. So when n value, the number of blows does not change, the soil is relatively maintaining its uh, uh, how to put it. So it is relatively maintaining its integrity. So there will not be much deviations in the shear strength of the shear strength of the soil when the slope of uh, this plot is higher. When the slope is lesser, there will be a the interval, that is the uh, interval of n between two water contents will be very high. So when water content changes from 20 to uh, for example 60 to 40, the number of blows will change drastically, which means that the soil is losing its entity and hence its shear strength. So the rate of change which is being asked in the question will be relatively lesser for soil A and compared to that of soil B. So option B is the right option. Am I clear or there is any confusion? Please respond.
Clear, sir.
Okay. So moving to the next question. If anybody has any confusions, please let me know. You are free to interrupt. Uh, and I will be there is no harm in explaining one more time. So but the objective of this session is to make the concepts that has been taught in the week more clearer, so that you can be proficient in the subject relatively. So now select the statements. So here it should be noted that it can be a multi-correct option question. So boiling point of bound water is greater than that of free water. Second statement is freezing point of bound water is lesser than that of free water. Third statement is viscosity of bound water is greater than that of free water. And the final statement is surface tension of bound water is lesser than free water. You have to say which statements are true.
1, 2, 3 is true. Fourth one is wrong.
Okay. Any other? Any other response? Or you are agreeing with this answer, or you have uh, any other opinions?
Yeah, sir, I agree.
Okay, first two are interrelated. So the boiling point and freezing point of bound water, uh, considering these two statements, what is the reason the for that two statements to be true? Why boiling point of bound water is higher and freezing point of bound water is lesser? Can somebody explain?
Bound water has a high energy.
Bound water does not have high energy. We need more energy to alter the nature of bound water. So, when it is a free water, when you boil it, and when it reaches 100 degrees, uh, which is the boiling point of water, it will start evaporating. But bound water has some attractive forces that binds the water molecules with the surface of the soil soil grains. So we need extra heat in case of boiling to break that bond between the soil grains and the water molecules. So that is why boiling point is greater for bound water. And in case of freezing, uh, this we since the attractive forces is higher, we need more energy, or we need to go to further lesser temperature to remove the energy from the bound water to make it freeze. So hence freezing point will be further lower. If for free water it is 0, it will be approximately 5 minus 5. It may go up to minus 10 also. And it depends on the mineralogy also, and uh, how strong these attractive forces are. And coming to the third option, viscosity of bound water is greater than that of free water. It is obvious that these bound water are held by attractive forces, and viscosity is the resistance offered by the fluid itself to flow. So hence, the bound water will fa- uh, will be relatively difficult. Will be will face more difficulty in flowing compared to free water. Hence, the viscosity of bound water is greater, apparently. And surface tension of bound water also will be greater than free water, but the statement is given otherwise. Hence, these three options are right. So, moving to the next question, same uh, type of question, identify the true statements. Phreatic line is the boundary between vadose zone and saturated zone. B,
Sir,
yes.
surface tension of bound water is greater than the free water. Once explain that statement is also.
Okay, so surface tension consider this as soil grains, two soil grains, and this is the absorbed water, and this is the free, uh, this both sides are absorbed water, and uh, consider another condition where there is no absorbed water, only free water is there. So every it when there is an absorbed water, the there will be an extra energy that you have to supply, or there will be an extra force which will bind the soil grains and what the absorbed water together. So whatever the process that you need to achieve, either be it boiling or freezing or movement or surface tension, in the sense capillary rise, you have to impart for more energy. So the reason for applying more energy is more forces are acting on it, which resists the action which you are supposed to do. So in that same notion, surface tension is also a force acting between the bound water and bound water and soil grains. Due to the increase in attractive forces, the in this case surface tension will be more for them.
Okay, sir.
So further to explain you more, see, this is the, if you consider this as a meniscus or capillary tube, if you if you derive an analogy between soil grains and capillary tube, there will be a surface tension acting on it, and this surface tension is further added by the attractive forces, which is not present at when there is no bound water. This will be zero. So this is the extra component which is getting adding up. So when you take this as a whole, this is the total surface tension component acting on it, and so due to the extra attractive forces, the surface tension of bound water will be higher than that of free water. I hope I am clear now.
Yes, sir.
Then moving to question 10, which of the following statements are true? Phreatic line is the boundary between vadose zone and saturated zone. Water in the vadose zone will be under tension. Water in the saturated zone will have higher pressure compared to that of phreatic line. Option D, all of the above. Can you answer the question? Which of the following statements are true? Can somebody respond? Am I audible?
Yes, sir, it's audible.
So, uh, can you answer? Can somebody answer this question?
Option A and option B is correct, but I don't know that statement. A and B is correct.
Any others? Okay. So we know that this is the water table, and maybe this is the ground level. So this is saturated zone, and this is Vadose zone, which is essentially an unsaturated zone with variable saturations, maybe. And part of it may be completely saturated also based on capillary action, but this will be saturated and completely below the uh, water table. So at this point, the pressure of water will be atmospheric. So phreatic line is the boundary between Vadose zone and saturated zone is the correct option. And water in the Vadose zone will be under tension, which is due to the capillary action. The water will be under tension. So option B is also right. Option C, water in the saturated zone will have higher pressure compared to that of phreatic line. So when you take the water table, this will be under atmospheric pressure. What will be the uh, press? Water have higher pressure in the sense that it is pore pressure. So what will be the pressure here at any point here? What will be the pore pressure? It will be equal to atmosphere or it will be higher than atmospheric pressure.
Higher than atmospheric pressure.
So this statement is also right. So the option is all the above statements are right. Hope it is clear now.
Yes, sir.
Okay. Now moving to the next question. So a river is 2 meter deep. The riverbed consists of a saturated sand with a unit weight of 20 kilonewton per meter cube. What is the effective stress at 4 meter below the top of the sand? It's a straightforward effective stress problem. Please excuse me for 1 minute. Meanwhile, you solve the problem. I'll be back in 1 minute. I'll be back in 1 minute. Have you solved the question? Please let me know if you have solved the question, or if you are facing any difficulties, please let me know. If you have solved the question, please let me know, or if you are facing any difficulties, please let me know.
Forty kp.
Okay. So answer is right, 40. So just for the record, I will explain it once. So this is the top river and this is the ground level. And this is given as 2 meters and unit weight is 20 kilonewton per meter cube. Obviously this whole strata will be saturated, and we need to find at a point, for example, let us keep the point A at 4 meter. So now we know that effective stress is total stress minus pore water pressure. Now total stress will be, if we take you can take gamma W is equal to 10 kilonewton per meter cube, or if it is in gram per cc, it is 1 gram per cc. Now total stress will be 10 into 2 plus 20 into 4 minus pore water pressure will be 10 into 6. That is 2 from water column and 4 from inside from the soil layer. So it will be 100, it will be 60, so it will be 40 kPa. So the option is 40 kPa. So hope it is clear. So it is a fairly straightforward question. So moving to the next question. So it comprises of various component, and by solving it you will get a comprehensive picture of the effective stresses concept. So a layer of compacted clay extends from the ground level up to a depth of 6 meters, and that clay layer overlies a 6 meter thick sand layer. let me draw the figure for your understanding. So this is the ground level, and this is 6. Please mute if you are not responding. And this is clay. Clay layer is overlaying a 6-meter sand layer. So this is sand, and this is also 6 meters. And again the statement is water table is at 6 meter below ground level. A 2-meter thick capillary saturation zone has been identified above the clay sand interface. That is, there is a layer in which capillary action is occurring, and the zone of complete saturation is for 2 meters. And the saturated unit weight of sand and clay are 19 and 20 kilonewton per meter cube respectively. This is 19, this is 20, and this is 16. Now, as a first initial problem, you please calculate the effective stress at 3 meter below the ground level. So this is dry. You can consider it as dry, and this is saturated due to capillary action, and this is saturated due to the water table. Can you please solve the first question now? That is first part of this question. Please solve it. And
48.
48, that is right. It is just 16 into 3, and this is the total stress, and pore pressure is 0 since the soil is dry, and hence it is 48 kPa. And second part, pore water pressure at 5 meter below the ground level. This is ground level. Please read the question carefully and answer. Pore water pressure at 5 meter below the ground level.
Pore water pressure is negative -10.
Okay, you have taken gamma W as 10, right?
Yes, sir. Gamma W 10.
Okay, everyone can take gamma W as 10 and solve this. By the way, that is negative. The answer is -10. So here uh, the point is somewhere at the middle of this layer. So that means 5 meter from ground level means 1 meter from water table. So here the capillary rise which we consider is Hc is 1 meter, and we know that in the capillary zone UW is minus gamma W Hc. So 10 into 1 will be minus 10 kPa. Please note, always in the capillary, if capillary problems are there, please do not fail to write the sign convention, or if you are not writing the sign convention, please denote in the bracket that either whether it is compression or tension. So now moving on to the next question. Total stress at 6 meter below the ground level. Total stress at 6 meter below the ground level. Please compute the answer and let me know. And if you are facing any difficulties, also please let me know. What is the value you are getting? Are you able to solve, or you are facing some difficulties?
I think 108.
Okay. Others? Is it 108?
104.
Yes, this 104. So total
Sir,
stress
104.
at 6 meters will be 16 into 4 plus 20 into 2. It will be 104 kPa. So now calculate the pore water pressure at 12 meter below the ground level.
Sir, I have a small doubt.
Yes.
At the total stress at 6 meter below the ground level,
Mm-hmm.
so 16 into 4 plus or 20 into 2, but uh, capillarity rise, the stress, the additional stress is also there. So
That
that's
is
not
that is
added.
that is when you are calculating effective stress. We are asking total stresses.
Okay, okay, sir.
Effective stress is where pore water pressure will come into picture. At that time, you have to consider pore water pressure. Now it is only total stresses. So now you can calculate pore water pressure at 12 meter below the ground level. Please compute it and let me know the answer. Or if you face any difficulties, please let me know.
60.
Okay. Any others? So it will be 60 only. Here we should note that the effect of capillarity does not come into picture when we are calculating here. So since if you draw the pore pressure distribution, the water pressure will be 0 here, and further there will be an extension which is gamma W into H, which is 6 meter. This is 10 into 6, which is 60 kPa. Now please calculate the effective stresses at 12 meter.
One double four kPa.
144.
Yes, sir.
Okay. So let us calculate this. Effective stresses will be first total stress, which is we have already calculated up to this as 104 plus 19 into 6 minus 10 into 6. How much you are getting? You will be getting
158.
158. So please check your answer once. If you have any confusions, please ask and get it clarified now.
So will we deduct capillarized water
No,
or
see,
not?
you are calculating pore pressure at this point at 12 meters. That is this point. At this point, if you take the pore pressure will be only positive. This negative we will not be considering
Okay.
because it already becomes 0 at water table, and then it is increasing. This increment in water pressure only will be experienced by the soil at 12 meters. Now you have opened an interesting point. Now you calculate the effective stresses at 5 meters, 5 meter from ground level. Now are you understanding? Now you will get why we are how what is the change you are observing when you are calculating effective stresses in capillary zone and under completely saturated below the water table. Can you calculate the effective stresses at 5 meter from ground level? Effective stresses. If you have calculated, please let me know the answer, or if you are facing any difficulties, please let me know.
74.
Okay,
74.
okay. So the total stresses will be 16 into 4 plus 20 into 1 minus what will happen to pore pressure? What is the pore pressure at this point?
10 into 1.
10 into 1,
Yes, sir.
it is in negative. So what will happen eventually? 84 plus 10, it will be 94. So that is the difference between pore pressure in capillary zone and pore pressure in below water table. So here water will be under compression. Here water will be under tension. Are you able to get it? So
Okay, sir.
you might have solved by taking the pore pressure as plus 10. So you are getting a value of 74. But in capillary zone, the pore pressure will increase the effective stresses. So it will bring the soil grains together. Effective stress is the stress that is transferred between two soil grains. So what is the physical significance if effective stresses are increasing? That is, the stresses through the grains are increasing. So water present in the capillary zone will will increase the stresses that is taken by the soil grains. So to explain in a very simple manner, you consider a container and you have soil grains in it. And which is completely, and you fill the container with water. All right. Now I would require some response from you. Now if you apply the load, you are applying a load which is which can be converted to a stress sigma. So this applied sigma will be uh, taken by which components? Are you able to get
Water
it?
and soil.
Water and soil. So the applied stress is total stress. The stress taken by the soil grains is effective stress, and the stress taken by water is pore water pressure. So this is how effective stress relationship is established. It is a fundamental common sense. So whatever, if you have two components, when you apply a stress, uh, the stress will be taken by both the components. So here when here in this normal case, uw will be we will con uw will be under compression, which we will consider as positive sign convention. Whereas in case of uh, capillary action, where water is tension, it will tend to it will tend to increase the uh, stresses through the grains. So pore water pressure will be negative. I hope I am clear now. Are you clear, or you are facing any confusions?
Clear, sir. Clear.
Okay. So if you have any doubt, it is a very important concept. If you are, this will be uh, following throughout the course of soil mechanics, that is geotechnical engineering 1, geotechnical engineering 2, as well as foundation engineering. Those who are from civil engineering background, this is the fundamental behavior, fundamental concept if you want to understand the engineering behavior of the soils. Now we are the discussion till now was based on index properties. Now we are slowly entering into the engineering properties and what are all the engineering phenomena that take place when uh, soil is subjected to an external load. So I hope that you are now able to realize the transition of the subject, how it is transferring. First you are classifying the soil and you are understanding, now you are understanding what happens when the uh, due to external loads. Now in the further sections you will be studying how the different soils that you have classified will behave to the same external load that you are studying now. So it is a kind of superposition principle kind of thing. You will be superimposing both index properties and engineering properties in the further in due course of the subject. So now let us go a step behind. So it is a little factual. These questions are little factual, and it is also required to know since these are as per Indian standard codes, and not only Indian standard, many standard codes. So well-graded sand should have uniformity coefficient, that is Cu, greater than 4, Cu greater than 6, Cc between 1 and 3, D10 greater than 1 mm. So it is a multi-correct option. So please keep that in mind and answer accordingly.
B and C.
Okay. Any others? Any other options?
Yeah,
Yeah, B and
yeah,
C.
yes, B and C.
Okay. If it is like this, how will you denote well-graded sand?
SW.
Yes, W. If what is the meaning of this one? It is well-graded
Well
gravel.
graded sand.
If
SW well graded sand.
SW is well-graded sand. If coefficient of uniformity is greater than 4, it denotes well-graded gravel. So that is a extra information. So as far as this question is concerned, we are concentrating on sand. So Cu should be greater than 4, Cc should be greater than between 1 and 3. And for gravel, if you replace this sand with gravel, A and C are the right options. So please note that also. So I hope it is clear now. Let us move to the next question. Soil having liquid limit and plastic limit as 40 and 20% respectively. Now, and the proportion of soil passing through 75 micron is 50%. Find the group index. So this relation is group index is related to soil classification by ASHTO. Let me give the relationship. So it is a little lengthy relationship. So group index, please excuse my handwriting. 0.2 into A plus 0.005 AC plus 0.01 B into D. So A is finer than 75 microns minus 35. Percentage finer minus 35. B is percentage finer than 75 microns minus 15. C is liquid limit minus 40. D is plastic limit minus 20. So please calculate each of the values and substitute it, and please let me know the answer.
Three.
3, there is no option. Will be greater than 3, obviously. Sorry for uh, uh, this one. So there has been a small mistake here. So
Yes, sir.
it is
I'm
3
getting
only.
3.
3 only.
Yes, sir.
Please change it. You can change the option A as 3. So sorry for this one. And so also, so what is the range of group index which we find it?
0 to 20.
0 to 20.
20.
Now, if the percentage finer, uh, let us say it is 30%. Now calculate the group index. Please change the percentage passing from 50% to 30%, and you calculate now.
-1.
But you said the range will be 0 to 20.
Negative value, then group index is 0.
So negative values, if there is a negative value, then group index will be denoted as 0. Please keep this in mind. Please do not forget it. So the option will be 3 here. And let us move to the next question. The ratio of given volume change in soil expressed as a percentage of dry volume to the corresponding change in water content. is known as? Option A, density ratio. Option B, mass specific gravity. Specific gravity of soil solids. D, shrinkage ratio. Please read the question carefully. Ratio of volume change expressed as a percentage of dry volume to the corresponding change in water content.
Shrinkage ratio.
Shrinkage ratio.
Shrinkage. What is the relation for shrinkage ratio?
V1 minus V2 by Vd by W1 minus W2 into 100.
Vd by W1 minus W2 into 100. So another one thing is, when this is under dry condition, it will be equal to mass specific gravity, shrinkage ratio. So that you can note it down. So moving to the next question. I hope it is clear. It is the given relationship has been given as a statement here. So it is just you need to convert the statement into the relationship and then you can answer this question. So moving to the next question. The effective size D10. Please note that if there is a term called effective size, it will be D10 of the soil X is 1/3 of soil Y, and void ratio E of soil X is twice that of soil Y. The ratio of the height of capillary rise HC of water in soil X to that of soil Y will be. Please calculate it fast. If you are facing any difficulties, please let me know. So this is soil X and this is soil Y. We know that capillary rise is inversely proportional to E into D10. Here if we take D10 X is equal to 1/3 D10 Y, and Ex is equal to 2 Ey, and Hc X by Hc Y will be equal to Ey into D10 Y by 1/3 D10 Y into 2 Ey. Are you clear now? You can cancel this. It will be 3/2 So which is 1.5. Are you getting the answer?
Yes, sir.
Others? So if you are getting the answer, it is fine. Otherwise, you can refer this. I hope it is readable to an extent. So the right option is 1.5. So is it clear?
Yes, sir.
Okay. Let us move to the next question. So this part we have covered. So you can just read it. It is the same value, 0 and 20. And here you can it is one of the uh, uh, you can solve this problem. Water table at a location is at the ground surface, and the saturated unit weight of the soil is 20 kilonewton per meter cube. If due to heavy rains, the water level rises to 2 meter above the ground level, the increase in effective vertical stresses at 2 meter below the ground surface will be. Please calculate it. Calculation is fairly straightforward. Yes.
Zero.
Okay. Any others? Any others? Okay. So the answer is 0. So just for once, there is an interesting result here. So initially this is the ground level. This is the water table also, and this is 20 kilonewton per meter cube. Now the effective stress at this condition is 20. Let us take gamma W as 10. 20 minus 10 into 2, which will be 10, 20 kPa. Now the water table is rising to 2 meters. and the ground level is here, and at the same point you are supposed to calculate. So sigma dash will be 10 into 2 plus 20 into 2 minus, sorry, 10 into 4 plus 20 into 2 minus 10 into 4. So this and this will cancel out. It will be 20 total stress plus 4 core water pressure. Just a minute. Sorry, 20 into 2 plus 10 into 2 minus 10 into 4. It will be 40 plus 60 minus 40 will be 20. So here, whenever there is a the there is a water level fluctuation, if for example you this is the ground, for example if you consider riverbed, and initially the water level is here, and for example due to flooding the water level is rising here. So due to these type of fluctuations, that is fluctuations of water level above the ground, please listen carefully. The fluctuations of water level above the ground will not have any effect on effective stress at any point below the ground level. So whatever be the water level above the whatever be the height of the water column above the ground level will not affect the change in water level will not affect the effective stresses at any point in the soil layer. Please remember this. If you come across any situations like this, you can straight away put the uh, uh, write the answer as 0. So please keep this result in mind. Please remember it to save your time. Also, obviously, you can calculate uh, and eventually you can arrive at that result. But in some cases, it might be better if you directly, if you are able to identify this. So due to the time constraint, I will be stopping here, and some more questions are there, which are relatively straightforward, and this you can solve it. The slides will be uploaded in there will be a section called problem solving session 2024. In that folder you can find the videos as well as the slides. So please go through those if you, for your reference, and please try to solve the other questions also. And if you have any doubt, you are free to ask uh, via the ask a question option or in the next problem solving session. Hope today's session was clear. You are able to you are clear with the questions. Please
Yes,
respond.
sir. Yes, sir.
Yes,
Yes.
sir. Clear.
So please, whenever you are facing any confusions, you can please ask me. You can ask either through the ask a question option will be there in your NPTEL account. Otherwise, in the next session, before the beginning of that session, you can ask this question. We can try to address those.
Okay, sir.
Okay. With this, we can conclude this session. Thank you. And this session uh, will be conducted every week on Saturdays, 5 p.m. to 7 p.m. And we will be solving the problems corresponding to the course corresponding to the content that has been covered in that particular week. So please go through the lectures before attending this session, as well as keep the calculators, as uh, these sessions will be mostly numerical, solving numerical type, that is solving problems. So thank you for attending. Let us meet next week.
Okay, sir. Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.